Very pleased to have Ian Tice from Carnegie Mellon, who is a good friend of our department and our group. We have seen over the years quite a few times. And he reminds me that it's actually 5 years since he was last here. Time goes by, but we're very glad that now you're here in person, and we'll talk about stationary and slowly traveling solutions to the free boundary Navier-Stokes equations. Thank you, Ian.
Thank you very much for the invitation. How do I make this go away? Okay, thank you. Yeah, thank you so much for the introduction, Susan. It is indeed, I think, my 4th visit here, and it's always an incredible pleasure to be back visiting you all here. So thank you very much for the organizers for the invitation. Let me also mention from the beginning here, so this is sort of a summary of 2 results. The first part is joint work with my CMU colleague, Giovanni Leoni. And the second part is work with Noah Stevenson, who is a graduate student at Princeton at the moment, but was my undergraduate at Carnegie Mellon. And if you will forgive the shameless promotion, he's a 4th-year graduate student and will be on the market soon. Remember the name. Okay, so let's get started. So this is a talk about Navier-Stokes free boundary problems. But for those of you who haven't seen me talk about this over and over again over the last decade, let me give you a reminder. The setup is that we have a sort of simplistic or primitive model of the ocean where we consider a layer of fluid in Rn, and I will label this layer omega of t for the time being, in order to indicate that it is a function of time. It's changing. And the general setup is something like this, where we will assume that the bottom of the fluid is completely flat. And in this case, I'm going to assume that the cross-section is infinite. So it's a copy of Rn minus 1 if I'm working in dimensional fluids. So meaning this is a domain in Rn, but down here, this is Rn minus 1. And I will label things so that the bottom is at 0 in the vertical direction. And I'm going to assume that when the fluid is quiescent, when it's not being acted upon by anything and it's basically at rest, it occupies a depth. So it'll be completely flat and will occupy a depth of b, where b is just some positive number. Then to keep things nice and simple, we're going to assume that the free interface of the fluid, which is the top part here, is a perturbation of B, and that the interface is a graph. So we're not doing anything as fancy as assuming that the upper surface is a manifold or anything like that. We're just going to assume the graph formulation as a perturbation of B. And I will, for the moment, describe this perturbation by a scalar function zeta, which will be a function just of the horizontal variable. That's what the prime means here, and of time. So the upper surface, which is the unknown, I will write as sigma b plus zeta. The lower surface is sigma 0. So the idea is that if the graph of something is being given, I write sigma of whatever the function is that gives me the graph. And then the domain itself, omega of t, is just a collection of points for which the vertical variable is bounded below by 0 and above by b plus zeta. Okay. So let's talk about the modeling assumptions. This is definitely a viscous fluid, and it's going to assume to be incompressible as well. And for simplicity, I'm going to assume that the density is 1. And I think in most of the talk, I'm going to be lazy and assume that the viscosity is 1 as well. I don't remember actually if I renormalized it, but if I set it to 1, that's fine. So the unknowns for positive time are the free surface function, which I already described. And of course, the reason we need to know the free surface function is because we need to know the domain where the fluid lives, right? We need to actually know where. So what I'm saying is this is a free boundary problem. So the domain itself is part of the problem. And in fact, for every time t bigger than or equal to 0, we need to know the velocity and the pressure, which are defined in this unknown domain, right? So we have to find the domain and the variables that describe its evolution. Now, the most important thing from the purposes of what I'm going to talk about is the various forces and stress that act on the fluid. So we're going to assume that there's a constant gravitational field minus GEN that's just pointing directly down into gravity, into the flat bottom orthogonally. We will assume that there is an externally applied bulk force, F external, that acts in the fluid, so in omega of T. And I will say quite a bit more about these in a moment, so don't forget these things. And there will also be an external surface stress, T external, which is defined on the free interface and taking values in the symmetric in-by-in matrices. This is really just a continuum mechanics thing that one typically thinks about applied stresses as being essentially symmetric tensors. It's not essential at all. And so if you just want to think about this as an arbitrary in-by-in matrix, that's totally fine as well. Another one of the main players is going to be the effect of surface tension, which is an effect on the free interface that is some fixed parameter sigma called the coefficient of surface tension multiplied by the mean curvature operator, which is the first variation of the energy functional. And this is a sort of restoring force that the fluid feels as a result of sort of deformations of the interface. Okay, so as a reminder then, if I include all of these forces and stresses, then the equations of motion are the standard incompressible Navier-Stokes equations with a free interface and no slip on the bottom. So now, okay, I have told you that there's gravity in the problem, but written in a very funny way. So let me point this out. So F external, I said, is a bulk force. So it should appear on the right-hand side of the bulk Navier-Stokes equation. But where has gravity gone? It's gone into this weird form here. The reason for that is a purely technical reason. And what it means is essentially I have taken the standard pressure that you would expect to work with, which would be this term, and I've renormalized it by subtracting off the hydrostatic pressure and then making another little quirky change in order to shift the gravitational term back into the bulk, but as the gradient of the free surface function. Okay, so I assure you this is a process that can be undone, and you can go back into the more reasonable formulation where you would have minus GEN on the right-hand side here. But this is relevant for the analysis going forward, so I like to write it in this weird form. Okay. Let me talk a little bit. So the first two equations here in the bulk are the standard Navier-Stokes equations. On the free surface, we have two equations that are really important. The first is the dynamic boundary condition, which tells you that the stress tensor, which is this object here, hitting the outward point at unit normal is balanced by the sources of stress on the surface, which are the mean curvature operator term that I mentioned before, and this external stress tensor. Okay, and again, I will say more about this in a minute, but for now, let's just assume that this goes here.
What is the eta that's sitting there?
The eta.
Is it supposed to be?
Where's there an eta? That is supposed to be a zeta. That's a ridiculous typo. Yes. Yeah, and okay. I've made the same mistake here. My apologies. So I'm going to immediately switch from zeta to eta, and that's what I've done here. My apologies. That is definitely a zeta. Okay, yeah, wow, that is confusing. I've just switched back and forth randomly between them. Sorry about that. Okay, and then so the other equation on the free interface is the so-called kinematic equation, which tells you how to update the graph function as a result of its interaction with the fluid. And this equation tells you that the time derivative of the free interface is proportional to the normal component of the velocity field, where the coefficient of proportionality is the area form on the boundary. And as I said earlier, we will impose the analyst's favorite choice of a boundary condition, the no-slip Dirichlet conditions on the bottom. Is this necessary? No, but I'm going to talk about this for most of the entirety of this talk. But there are other things you could do. Let me also mention this funny math BBD is just the symmetrized version of the gradient. So you take the derivative and add to it its own transpose, and that's what that object is. Okay, so this is not a talk about dynamic Navier-Stokes. This is a talk about traveling waves or stationary Navier-Stokes. So let's say what that means. So the setup here is that we're going to assume that these terms F external and T external, which I keep talking about as being important, are stationary, meaning that they are time independent in a coordinate system that is moving parallel to the bottom of my fluid. So, for instance, if the bottom of the fluid were the floor here, like it would be stationary, just moving along at a constant rate like this and somehow acting on the fluid, right? So that was my pantomime of an external stress. Now the fully stationary problem corresponds to what happens when gamma is 0. The thing is not moving, it's just sitting there. And of course, something like this would be relevant if you're thinking about long-term dynamics for the dynamic problem and thinking about what happens when time goes to infinity. So for instance, if you look at the dynamic problem and there are components of F external and T external that don't decay, then you expect these things to play a role in the long time limits. Okay, so why in the world would I want to include this F external and T external? What would they model in this traveling waveform? There are a couple different ways of thinking about these. Some more convincing than others. My personal favorite is to think about the external stress as a tube of air blowing on the fluid, or maybe a very small ship moving at constant speed across the surface of the ocean. If you don't like that, that's fine. You could also think about this as an extremely primitive model of wind, where the wind is moving across the ocean at a constant speed and acting on the fluid. Those explain how you can think about the external stress. How do you justify F external and its action on the fluid? Well, I like to think about that as a locally moving perturbation of gravity, as you would get from, say, the moon moving across the completely flat ocean. Right, so this you could think of as an extremely primitive model of how the tides are generated. Extremely primitive because it's obviously ridiculously false, but it's something like a satellite or the moon moving over the ocean. Okay, so now the idea is that I'm going to put these things in traveling wave ansatz form. So T external is just some fixed T that will be independent of time, and I will write it in this form. Same thing with F, and I'm going to make exactly the same changes for the free surface function. So this is how I will switch to eta for the velocity, and I will switch to a vector field U for the stationary velocity and P for the stationary pressure. Now this will remain in free boundary form. I still don't know this function. It's just that now it's time independent. Right, so this problem is going to be phrased in this unknown domain omega of B plus eta, where I need to figure out what eta is. Okay, now here's the little cartoon of what I was describing. So, you could think about this as a situation where you have a fluid and the tube is blowing on top of it, blowing air on top of it, and then being translated across the fluid. And that is how you can think about what T is doing. And as I said before, you can think about F as being a sort of perturbation of the constant gravitational field that you feel in the bulk. Now, why have I drawn this ridiculous cartoon? Well, because it's my attempt to, make a cartoon of this beautiful experiment that was done by these people here, and I have stolen this from their paper, and they did precisely what I described. They took a wave tank full of a viscous fluid, they mounted a tube on a motorized rack, and this tube blew air on the fluid as it moved at a constant rate. And they put a high-speed camera in the same frame and took pictures. And what they were able to see is that in certain parameter regimes, when the tube was moving at certain speeds and the viscosity was certain parameters, that they actually saw coherent structures, aka traveling waves, in that frame. And you can see that the shape of these things changes dramatically as they increase the speed. Initially, it's just a sort of lumpy thing, but eventually you get something that almost kind of looks like a shock. There's a sort of V-shaped structure that forms. And these are taken, again, in the moving frame, and the speed is increasing as you go from A, B, C, D, E, and F. So these are moving much faster than these ones over here. And yet, over this full range of over a large range of speeds, of traveling wave speeds, they were able to observe the existence of structures. So this isn't just a complete hand wave. This roughly corresponds to an experiment that was done. Okay, so when I make this ansatz, all that happens is the time derivatives become minus gamma d1 derivatives, meaning derivatives in the e1 direction. So the time derivative term that I previously had in Navier-Stokes becomes this guy here, and the time derivative that was in the kinematic equation becomes this gamma d1 here. The only other thing that I have changed as I move through here is I've gotten rid of the standard normals and replaced them with the non-unit normals, just because it's slightly easier to think about what's going on. Okay, so as a reminder, the fully stationary problem, the sort of time-independent unmoving problem, corresponds to gamma is equal to 0. The other thing that I want to point out is a very deep mathematical observation that if I take any gamma, no forcing, no applied stress, then my solution, or then I have a trivial solution 0, 0, 0. Okay. Now this is part of the reason why I have normalized this in this way by sticking this here, because now everything has 0 as the solution rather than hydrostatic pressure as the solution. But in fact, unsurprisingly, if I assume my solutions live in essentially standard Sobolev spaces, and there is some wiggle room here, but I need some sort of Sobolev framework, and I assume that the applied stress and the applied force are zero, then in fact you can prove that the velocity is zero, the pressure is zero, and eta is zero, which means that it's quiescent. Yes?
Can you explain again why do we see gamma E1?
Sure, because the ansatz assumes that the thing is moving at a constant speed in the E1 direction. So time derivatives become E1 derivatives.
Oh,
Yeah, so the thing is moving parallel. I think I said it was moving parallel, but I didn't explicitly say. Up to rotation, because the problem is rotationally invariant, I can always assume that that direction is E1. Why E1? I'm labeling. Okay, so anybody who sees this and has thought a little bit about Navier-Stokes should be completely unsurprised by this, in the sense that Navier-Stokes is a dissipative system. The dissipation mechanism of viscosity removes energy from the system, from the fluid. And so naively, the only way that you would expect a persistent structure like a traveling wave to exist is if you have a source of power that balances the dissipation rate. And that is precisely what T and F are doing. They are providing a source of power that the dissipation can then dissipate. And those things being in balance with each other allows for the existence of these structures. Well, among other things. Okay, but at the very least, what this is saying is, so I've made a big deal about needing T and F because without them, there's just triviality. Okay, so you need to drive the system in order to get solution. Let me tell you a little bit about the history of this problem. This problem goes back to the very beginning of fluid mechanics. Even Stokes was thinking about this type of problem. However, mostly for the inviscid problem, where the viscosity is equal to zero. And there are literally hundreds, if not thousands, of papers in the literature on this, so I will not be able to tell you much. But suffice to say that in the mathematics literature, the story really gets started about 100 to 120 years ago with analysis of the two-dimensional periodic and irrotational problem, again for inviscid. And this concluded after about between 60 and 80 years worth of work with a proof of the Stokes conjecture, which was sort of constructing traveling waves that are periodic and have a certain extremal condition associated with them. About 20 years ago, starting with the work of Adrian Constantine and Walter Strauss, the rotational problem finally was cracked. And their school has been quite successful in continuing to attack this and prove many more things about this over the last 20 years, including even some work with some sort of primitive but related models of surface forcing. In the inviscid literature, though, there is very, very little in 3D. This is not far from all you can find. It turns out that the 3D irrotational, the 3D inviscid problem is quite a bit harder than the 2D inviscid problem. When I started working on this problem back in 2018 or so, I couldn't find anything in the literature about the viscous problem other than a couple results vaguely related to this stationary problem, but in domains that are not really the same as ours. But I was able to find, these more recent beautiful results that I mentioned earlier, and the one I showed you is not the only one. There are several groups that have produced pictures like this. So these were reproducible experiments. Again, about 5-6 years ago, I started working on this with my colleague Giovanni Leoni, though the paper has only recently appeared in CPAM. But the result says the following. So we can either consider the case when n is equal to 2, so we're in 2 dimensions, and surface tension is either on or off, or we can consider general dimension n bigger than or equal to 3, and yes, we do bother to consider 7-dimensional fluids. It's mathematics, so who cares? But in this case, we have to turn surface tension on. But the theorem says that given the dimension, there exists a regularity parameter S, and such that the following are true. So the first is that we can find a non-empty open set WS that is contained in the space where we would expect the free surface, the traveling wave speed the applied surface stress and the applied force to live. So here, gamma lives in R, delete the origin. T lives in this standard Sobolev class, and F lives in this standard Sobolev class. And we can find a Sobolev type Banach space XS. This is where the solution UP and eta are going to live, such that the following are true. And I will say more about this in a moment, but I'm being vague about it intentionally now. So the first thing is that our curve of trivial solutions lives inside here. The second is that this space XS is sufficiently nice that every solution that we manage to construct in here will at a bare minimum have regularity where the velocity is C2 with second derivatives bounded, pressure in C1 with up to first derivatives bounded, and the free surface is C3 and everything decays to zero at infinity. So what this means then is that if we manage to construct a solution in here, it's a classical solution. There's no weak formulation here. But the crux of the matter is item 3 here. Given any traveling wave speed gamma that's not equal to 0 and a t and f in here, there exists a traveling wave solution up and eta, which solves a flattened equivalent reformulation of the problem classically. And these solutions are locally unique, satisfy various nice estimates, and you can go back into the Eulerian coordinate system by unflattening, and you will have a classical solution there. So everything here is a nice classical solution. And moreover, we can prove that the map that takes the data tuple gamma TF and maps it to the solution is continuous. So it's really a well-posedness theory. We're showing that the solution depends continuously on the speed and the forcing and stress terms. Okay. Now, this is a bit of a weird global way of thinking about this with this WS. If you prefer, you can think about it in a slightly more reasonable way where you say, fix any gamma not equal to 0. Then what this tells us is that there is an open, non-empty set in these Sobolev classes of data near the origin for which we can solve the problem, and we can solve it uniquely. Okay, so what that's saying is every speed other than 0 gives us solutions and gives us an open set of data for which we can produce solutions. Okay, so here are some remarks on this. Now, as you will perhaps be unsurprised to hear, given the structure of what I just wrote, the proof is based on the implicit function theorem. Moreover, we know that the solutions decay as you go out to infinity. So the velocity field and the pressure also decay as you go out to infinity. So these are what we call solitary waves in the traveling wave literature. So these are not periodic solutions. With a little more work, which we don't really bother to do in the paper, but is relatively easy, you can also prove continuous dependence on the gravitational and viscosity parameters. Though, of course, you cannot send them to 0. They need to remain positive. And as I said, this is work that's about 5 or 6 years at this point, 5 or 6 years old at this point. We've been quite busy doing more on this with Noah Stevenson and Junichi Kogunamaru and Hui Win. So we were able to do the same problem, but with multiple layers of incompressible fluid, provided that they satisfy the Rayleigh-Taylor condition. We were able to look at the problem where you add incline, in which case you have to, instead of perturbing around the standard hydrostatic pressure, you have to have shear flow solutions that you perturb around. That makes things a little bit more interesting. We were also able to include effects of periodicity, both in the direction of propagation of the waves and transverse to that, and to see what happens. There's some subtlety there. I said earlier that it's not necessary that we use no slip at the bottom, because with Junichi, we were also able to study the problem with Navier slip on the bottom and show that we could send the slip parameter to 0 and recover the solutions with no slip. In collaboration with Hui Win, who's at Maryland now, we were able to do the Muscat version of this problem, or if you prefer, the Darcy law version of this problem. And in this context, we were actually able to also prove some dynamical stability results, which were quite nice. We have not been able to do dynamical stability for anything related to free boundary Navier-Stokes yet. With Noah, we also were able to do the compressible version of this problem, which sounds like, you know, it should be easier in the sense that you drop 2 of the letters, but is in fact massively harder because the density evolution equation does not have any ellipticity associated with it. And so no standard implicit function theorem techniques were available, and we had to bust out the really heavy guns and develop a Nash-Moser scheme. But once we had the Nash-Moser scheme, we were then able to utilize it to attack a version of the so-called viscous shallow water equations. And in that context, we were actually able to establish some inviscid limits, which are kind of interesting. One thing I want to emphasize here is that our technique does not work when gamma is equal to 0. So I have said several times now that we need to eliminate the possibility of the traveling speed being 0. This is not for convenience. It's actually a technical obstruction in our work. And the reason is that the parameter being not 0 plays an essential role in defining the topology of this space that I haven't yet told you, but this is where the solutions live. And the reason for that is because this space involves a very strange new type of anisotropic Sobolev space, which I'm now going to sort of give you a quick tour of. So, as I said, we solved this problem via the implicit function theorem by perturbing around the trivial solutions. So what does that mean? That means we're going to need to linearize around the trivial solutions and understand the corresponding linearized problem. So if I do that, if I linearize around the 0 solution, and I also am going to rewrite the problem in the equilibrium domain Rn-1 crossed with 0b, I end up with the following linearized system. Now, this looks very, very similar to what we saw before, so I don't want to spend too much time on it. The only real point is that the mean curvature operator linearizes to the Laplacian. But what I want to point out is I want to underline where we see eta. Here, it comes with a gradient. Here, it comes with a derivative in the E1 direction. And here, it comes with a Laplacian. And these are the only 3 places where we see the free surface function. So what that means then is, based on the story as I have told it here, the sharpest estimates that you possibly should expect in standard Sobolev spaces, meaning if, let's say, I assume that this F is in the Sobolev space HS, then what would I expect naively? Well, for instance, I might expect U to be an HS plus 2, etc., P to be an HS plus 1. Well, the best estimates that I can get are that the gradient of eta is going to be an HS. Gamma times the first derivative of eta is going to be an HS plus 3 over 2 and an H dot minus 1. This maybe is not so straightforward, but it's going to come from this equation together with the divergence free condition. So just trust me, you can prove this. And that the Laplacian will be in the space HS plus a half. Okay, so this is a real hand wave. This is just sort of formal derivative counting. Making this rigorous is actually quite delicate and required the rather brutal computation of the symbol of a particularly nasty pseudo-differential operator that took Leone and me about 6 weeks of work just to compute this thing by hand. So it's not so easy to justify this, but it is true. But the point is that once we sort of know that this is the best that you can get, well, this is the best that the problem is telling you, or is giving you access to, so you sort of assemble it into a norm, and what you get is the following. So if the dimension is 3 and higher, then at least as long as surface tension is on, I get control of the following quantity, where I'm looking at things on the Fourier side, and I'm splitting into the unit ball of low frequencies and then everything else. Okay, and at high frequencies, you can see this is like a standard HS plus 5 over 2 norm. So I'm getting control of the HS plus 5 over 2 norm of the high frequency part. But at low frequencies, this is a very strange multiplier that's anisotropic in the sense that it has this C1 squared term sitting in front of it. And then if you look at what happens here, this this washes out and gives me like a C squared term. So for instance, if you're in 3D in the bulk, you're in 2D on the cross section, and you could think about this term in polar coordinates as like R squared plus cosine squared theta, which is a bit of an odd multiplier to have on the Fourier side. Now, notice that if I'm in 2 dimensions physically, which means I'm in 1 dimension on the cross section, then C1 is equal to C. And these terms cancel out, and lo and behold, I get standard Sobolev control. Okay, so in dimension 2, oh, and there's one other thing that I should point out here, and it's a technical miracle in 1 dimension, which is that any derivative is an elliptic operator in 1D. So if you stare at these things in 1 dimension, these equations are of equal strength. And what that means then is that in 1D, I don't need to rely on 1D of the cross-section, I don't need to rely on the surface tension to do the heavy lifting at high frequencies. I can rely on the transport operator to do that. Okay, So what does that mean? It means that if the ambient dimension is 2, the cross-section is 1-dimensional, and I can use standard Sobolev spaces. But I don't want to just restrict to 2D. I want to do 3D. So I'm stuck with using this weirdo over here, and there's no arguing with it. This is the best I get out of the estimates. Okay, so the question then becomes, and in fact, let me point something out here that I'll say again in a minute. Gamma not being equal to 0 is essential here. Why? Well, because it gives me this term. Who cares? I'll tell you in a second. But if it weren't there, then the best I would get at low frequencies would be like c squared times eta hat squared, which is like being an h1 dot in 2D, which is critical. So the best you could hope from that would be BMO for the free surface function. But in fact, h1 dot is not even complete in 2 dimensions. So there are much more nasty problems lurking under the surface here. Okay, so it's really crucial that we have this extra little bit of control. Okay, and the reason is because we can just say, well, look, this is what the problem is giving us. Let's not argue with it. And let's define a new type of space with this norm. Now, I've thrown the parameters away because, well, I don't need them anymore. I just need them to be equivalent to 1. But at high frequencies, this is just a standard Sobolev space multiplier. And at low frequencies, it's this strange anisotropic multiplier that comes from my problem. So what happens? Well, this is a Hilbert space that is strictly larger than the standard Hilbert space HS, at least when so here I'm calling the cross-section RD just to make things simpler. So D is really in -1 for the fluid. But so this we can prove is strictly larger than the standard Sobolev space. And in fact, one of the ways that we prove this is we prove the strange fact that this space XS is not closed under rotation. So the idea is you can take profiles that are in this space that are somehow biased toward the direction of motion, and you can rotate the profile by theta for arbitrary theta and leave the space. So somehow the space is very tuned to the fact that things are moving in the E1 direction. And moving at an actual speed, not sitting there. But a technical miracle occurs, which is that the reciprocal of this quantity here is integrable. And what that means then is that I can take the functions that are in here and on the Fourier side, split them into low frequency parts and high frequency parts. This condition tells me that the low frequency part is going to be an L1 and it's band limited, which means that it is smooth and all of its derivatives go to 0. The rest is a standard Sobolev space. And so what that means is we're in a space that is definitely bigger than standard Sobolev, but it's not so bad in the sense that everything that is in there is standard Sobolev plus something absolutely beautiful. Okay. Then, because we need to use this with an implicit function theorem argument, we need to prove lots of functional analytic at the linear level and nonlinear functional analytic properties of this space. So we need embedding properties, which continue to hold. We need some nice product and composition structure. At some point in this story, we also needed to prove that this space is an algebra, and we characterize when that is true. That is not a trivial fact and requires some really nasty Littlewood-Paley theory. Etc. But the point is that once you recognize that this space is there and needs to be worked with, in fact, it allows us to identify an isomorphism for the linearized problem that I showed before. And once we have the isomorphism in hand, we do some nonlinear work, and then we can invoke the implicit function theorem and get our solutions. Okay, so this is the story of the older problem. Let's talk about what happens now with the stationary problem when gamma is equal to 0. Okay, so I've just told you that gamma is the hero of the story. What happens when the hero dies? Well, in this case, the best that's going to happen when the dimension is, let's say, 2 or 3, is that instead of having the estimates that I wrote here, we will just get that the gradient is an HS plus 3/2. Okay, so you can think about this as a loss of control at low frequency, because of course what this means is that in some sense at low frequencies, the best that we know is that eta is an h.1 in 2 dimensions, which again is not even complete. But of course you could say, oh, who cares, just complete it. But if you complete it, then what you get is a space of tempered distributions modulo constants. And this function eta is supposed to give us a graph is supposed to generate a graph that we use as the boundary of a domain. We cannot use a tempered distribution modulo a constant to generate a graph, right? So the point is that this is an absolute disaster if we try to just complete this. Okay, so we have to have something to work with here. Moreover, in this context, when we have gamma is equal to 0, we don't have a good isomorphism, and it seems that the nonlinear estimates that we would want to close the implicit function theorem argument aren't going to work. Okay. Well, so Giovanni and I, in our initial work on this, just said, okay, well, fine. The stationary problem doesn't work. We'll kick this down the road. Well, so then Noah started thinking about this, and he made the following observation, which was to say that, and let's just focus on 3D here. Okay, so let's assume n is equal to 3 and gamma is equal to 0. And what Noah said is, well, suppose we could somehow retool our functional framework so that we were not working with L2-based spaces, but slightly subcritical. So we could drop the integrability index to R for R strictly less than 2. Well, in that case, let's say we were to assume that the gradient is an HSR and the Laplacian is an HS plus a half R, where these spaces now are the Bessel potential spaces that I've defined here. These are the standard sort of Fourier analytic Sobolev spaces with integrability not equal to 2. Well, then the crucial observation is that in this context, you can use a homogeneous subcritical Sobolev embedding that was proved by Hailash and Kelemaishka back in '95. And what it would tell you is that because you have dropped into this subcritical regime, your function eta will in fact hop up into some standard Lebesgue space. And if you combine the indices in the right way, what you will then get out of this is that eta itself is in some standard Bessel space, Bessel potential space. And then if the numerology is right, you can then use that to guarantee that you not only have a function, but a continuous and bounded function that goes to 0 to infinity. So the whole point of this is if you could somehow retool the functional analytic framework to not work in L2-based spaces, but LR-based spaces, there would be some hope for this working. Okay, well, there is a long history of people making similar observations, and in particular working on the Stokes problem in LR-based spaces, mostly involving the sort of German school around Helmut Abels and the Japanese school involving Abe and co-workers. But the problem with these results, and not that there's anything wrong with them, but the trouble with trying to use these results in our context is that they are heavily based on pseudo-differential or Fourier multiplier techniques that require explicit knowledge of the symbol for your underlying linearized problem. And for us, this is in some sense the entire problem, is that computing this symbol with the traveling wave speed or with the free surface is very, very difficult to do explicitly. And in fact, this is the thing I alluded to earlier, that it took Giovanni and I about 6 weeks to actually do this by hand at some point. And this was just for one part of the symbol. So the observation now is that, well, maybe we don't need to actually compute the full symbol, but we could instead try to take inspiration from this set of ideas. And in particular, we can make the observation that the full LR-based framework is in some sense overkill, because in fact we have we only really need LR in the horizontal directions, because this problem is entirely due to the free surface, which is just on the cross section. Okay, the framework that actually ended up working is as follows. So given a vector space V, we're going to define a strange mixed type functional framework. Excuse me. And we'll write it as LR comma 2. And what you should think of is that this is LR in the cross section, which is RD in this context, with values in L2 in the vertical direction. Okay. Now, once you have identified this sort of basic Lebesgue space, you can define a Sobolev space tuned to this. And so we define HS of this to be the set of things that are in LR2 for which the derivatives up to order S live in the same space as well. So basically, we're imposing LR type integrability for these derivatives in the horizontal direction, but L2 integrability in the vertical direction. Okay, now to implement this subcritical trick that I mentioned earlier, we also will define this tilde gradient space. This is the set of things on the cross section that are in whatever the appropriate Lebesgue space is, whose gradient is in this Bessel potential space. And then this embedding result that I said earlier can be implemented in this space, and this tilde space, which is where we will construct the free surface, will embed into CK spaces as you would expect. Okay, so the result with Noah, which came out just this last year, is that if we only look at dimension 3, and that's the only thing that we can consider, but we pick any r between 1 and 2, then there is a regularity parameter that is tuned to r, and open sets like what I was describing before. So there is an open set in the data space, but notice now that it contains the origin. And there's an open set in the solution space, but this is roughly mirroring what I showed you before. Well, actually, I didn't actually tell you what this was before, but this is roughly similar to what we had before. It's just that now these are LR based in the horizontal direction rather than L2 based. But we identified these appropriate spaces such that we can prove something like what Leone and I proved. So that is to say that for every gamma, T, and F in this space, there exists a either traveling or stationary, depending on whether gamma is 0 or not, solution to the problem. They're classical solutions. You can unflatten them. They're locally unique and they obey various estimates. And moreover, this is a well-posedness theory. So in fact, we can show that the solutions depend continuously on gamma, T, and F. In particular, the most important thing about this is that gamma equals 0 is allowed here. So we can actually solve the stationary problem now. Yeah.
For NES greater than 3 over r plus 1, right?
Yes. Yeah. Potentially you could do slightly better than this, but this is chosen for minimal convenience. Yeah. Okay, so we also prove that the solutions are continuous with respect to the various physical parameters, gravity, viscosity, and wait, what is kappa? There is no kappa. That came along for the ride. Yeah.
So what's the regularity of the pressure in the area?
That guy right there. So H1 plus S R2, this means that it has 1 plus S derivatives, and they are LR in horizontal directions, L2 in vertical directions. The velocity field is in 2 plus S.
Then embeds to C1. H1 plus S R common to.
Yes.
And so in the equation you have gradient of pressure, which is going to be C0, right? Continuous.
Sure.
So how do you come back to the Eulerian coordinates?
Because, okay, so all of this is, I haven't told you, but there is a flattening map that we use to go back and forth between the original Eulerian system and the flattened system. This flattening map is determined in terms of the free surface itself, which will have regularity higher than what you're describing there. And so it will be for lack of a better term, in the counting scheme that we're using where the pressure is C1, the diffeomorphism will be C2. So it'll be good enough to preserve the C2-ness here, the C1-ness here, and then you don't have to, nothing gets transformed for the free surface function. Yeah. But yeah, I mean, you are on the right track in saying that these parameters are tuned basically to make sure that you're above all of that threshold. Because of course, if you produce solutions in the flattened system that you can't go back to Eulerian coordinates and verify, solve the problem, you've done something a little wrong, right? Okay, so not only did we solve the problem for gamma is equal to 0, which of course was what we wanted, but the nice thing about this is that this open set here is open in the reals and contains the origin. So we don't claim that we solve it for all gamma like we did before, but we at least can say the following. So every stationary solution that we are able to construct here actually lies along a continuous one-parameter family of traveling wave solutions. So the way I like to think about this is that tube that was blowing air is moving at a speed, and you have a little dial in the laboratory that can slow it down, and it comes to a halt, and the solution adjusts continuously as you're doing this. Okay. One thing I want to point out though is that when gamma is not 0, when you're in the rest of this curve, we actually get a bonus estimate. So you can come back and do an a posteriori estimate in this context, and we will learn that gamma times the Riesz potential, or the Riesz operator rather, in the E1 direction, hitting the free surface belongs to LR. And this might seem completely out of the blue, but we've seen this already in the sense that earlier I said that we were able to prove that gamma times d1 of eta was an h dot minus 1. And this is in the L2 based setting. And if you think about what that means on the Fourier side, it means that C1 over the absolute value of Xi is in L2. Well, that's telling you precisely that the Riesz operator acting on this thing is in L2. And so what we've recovered is a sort of lower integrability version of that condition. Okay, so morally, it's a very similar result, at least when gamma is not 0. So what that means is you can kind of think about this as a sort of singular limit in the sense that we have identified a big container space that works for a range of gamma around zero and including zero. But when gamma is not zero, the solutions actually live in a strict subspace where you have this extra bonus control. And then as gamma goes to zero, that extra control degenerates, and then you just stay in the bigger space. So it's a sort of singular limit. Now, the one thing I want to point out is, so this technique does handle the case when n is equal to 3, but unfortunately it does not handle the case when n is equal to 2. So we're still stuck and have absolutely no idea how to do this problem. Even the wishful thinking is going to fall apart here. Okay, and I have like 10 minutes left, is that right? Okay, in the time that's left, let me give you a very brief overview of the strategy for how we attack this new stationary problem. So the initial observation is to go back and hack the linear problem. Part of the problem that we have when doing analysis on the original version of the linear problem is that we think of eta as a function, and then the gradient of eta appears over and over, and the Laplacian of eta appears. But eta itself doesn't. So the new approach is to just say, well, let's just forget about eta altogether and replace gradient of eta with a generic two-dimensional vector field. Now, fine. What that means then is that, remember I had a gradient of eta appearing in the bulk equation, so I just put that guy in the bulk. On the boundary, I had a Laplacian of eta, which is of course the divergence of this x prime. But now I want to maintain some sort of ellipticity, so in order to do this, what I'm going to do is I'm going to cheat and augment the problem with yet another PDE, because I've introduced, in some sense, too many unknowns, so I'm going to add another unknown. And I'm going to augment the problem with an applied curl equation. So in some sense, what I've done is I've now made a div curl system that couples to my original problem. And the crux of the matter is, if I take omega to be 0, then the curl of x is 0, which tells me that it will be the gradient of something, and I'll be able to go back to my original problem. Okay, so I've embedded it in a bigger problem, but it's a problem for which I can come back. Okay, now the thing that's nice about this is, well, I mean, div curl is a nice problem, and I already knew that there was a relatively nice problem associated with most of this. So in fact, we get a relatively satisfactory L2-based well-posedness theory. And what I mean by relatively satisfactory is what we care about is we get an isomorphism between Banach spaces. So we're good to go. So what do we do next? How do we get to the LR approach? Well, first we start with the following observation. The type of Sobolev spaces that we were working with are HS spaces on this domain omega, which remember is R2 crossed with a finite interval. Well, there's something very nice that happens in that context. This space can be written as the intersection of horizontal HS with values in L2 vertically with horizontal L2 and values in HS vertically. Okay, this is an old interpolation result. And now the point is I can think about this as HS of the cross-section valued in some Hilbert space, intersect L2 of the cross-section with values in some Hilbert space. Okay, that's an observation. But the crux of the matter is, if I come back and look at this linearized problem, it's translation invariant in the horizontal directions. So that means I can invoke some tools from harmonic analysis and learn that the fact that this commutes with horizontal translations tells me that the solution operator has to be given by a Fourier multiplier. Now, it's not a pointwise Fourier multiplier, which is what I would get if I were legit on just a cross-section, just like just working on a problem on R2. But the solution operator is sort of working in these function spaces that are defined on the cross-section with values in Hilbert spaces. So what I end up getting is the solution operator is an operator-valued Fourier multiplier, where I think about it as a function of xi, of the horizontal cross-section, taking values in the space of linear operators between these Hilbert spaces. Okay, so the goal then is to say, well, look, if I have my hands on such an operator-valued multiplier, I would like to go back and remember my basic harmonic analysis and say, well, there's a beautiful theorem about these things called the Miklin-Hermander multiplier theorem. If I could make a variant of that would work for these operator-valued symbols, then I would be good, and I would be able to get estimates in something that looks that is our LR-based framework. So I would be able to get estimates in spaces that are Bessel in the horizontal directions with values in L2, and then LR in the horizontal directions with values in HS. Okay, now it turns out that this space that I just described is exactly the weird mixed type space that we choose to work in. Okay, so that's where this choice came from. Okay, now, as is usually the case, you would like to find an off-the-shelf version of a theorem that will do the job. None exactly works, so we had to build a custom version. This could, in fact, be its own talk, but I will just wave my hands and say, Noah went off to Princeton and became an expert in harmonic analysis, and so he came back and knew how to do this. The task now becomes showing that you satisfy the hypotheses of Mikl and Hermander. Now, the problem is that Mikl and Hermander says you need to know that the symbol is smooth or at least some degree of differentiable away from the origin and satisfy certain estimates. Now, typically, if you want to show that something is smooth and satisfies something estimates, you need to be able to write that thing down. And this is precisely the problem here, is we don't want to have to compute this, and in some sense, we don't really know how to compute it. So it seems like this is never going to work, but there's a very cute observation that pops out, which is that if I want to understand the differentiability of the symbol M, it suffices at first pass to understand translations of the symbol M. Right? Now, translations of the symbol M, which I'm writing here as M acting on D plus zeta, where zeta is the translation in the horizontal direction. These things act beautifully in the sense that they are the same thing as my original solution operator, but conjugated by complex exponentiation. So it turns out that so what I'm saying here is the operator that corresponds to sort of taking M of Xi on the Fourier side and translating it by zeta, the operator that I get from that is exactly the same as the original operator, but with these two conjugates, just multiplication by exponentials built in. When you have this observation, if I understand how translates work, then of course I understand how derivatives work. And I can try to use my understanding of the symbol for T, sorry, not the symbol, the mapping properties of T in order to deduce differentiability properties for M. Okay? And miraculously, this works. And you can actually iterate this and prove that not only do you get differentiability of the symbol M, but you get analyticity of the symbol M away from the origin. And not only do you get that, but you get the estimates that you need in order to prove Mikl and Hermander. And you get all of this for free without ever being able, or without ever having to compute the symbol itself, just based on the L2 estimates for the operator T. Now, when we worked this out, I said, look, someone has done this trick before. Hermander must have known this because he knew everything. But I have not been able to find this trick used anywhere. If you have seen it somewhere, please tell me, because I would love to know if it has been discovered before. Because the point is that this is an extremely general technique that should be useful for many other problems when you have either a full symmetry or a translational symmetry, and for whatever reason, you can't explicitly compute the symbol of your operator. But you would like to understand its smoothness properties. But this trick is completely generic. It works in complete generality. Okay, so the final two steps, and I will be quiet, are once we have established this, final step, and then I will be quiet, is that now that we have this, we can actually invoke the Mikl and Hermander theorem to show that this linearized problem that I wrote here actually induces an isomorphism. And once I have that, I can undo the vector field swap by imposing the curl-free condition. And so that will actually allow me to solve the original problem that I wanted to solve in the LR-based spaces. However, the caveat is because I'm using harmonic analysis tools, which are built on interpolation, I can never do the case when R is equal to 1. And this is why the dimension 2 problem is still open, because you would need to drop down to R is equal to 1 in that case. So we have no idea what to do then. Harmonic analysis will not come to the rescue. Well, maybe it will, but not this harmonic analysis. So then the final task is so all of what I've told you is essentially how to build the functional framework for the stationary problem, but I told you that we're able to actually solve the traveling problem as well in that context. This involves a trick at the nonlinear level where we somehow embed the traveling problem into the stationary problem by use of another operator defined via a Fourier multiplier. Unfortunately, this one is not of Miklin-Hermander type, and so once again, Noah's harmonic analysis knowledge came to the rescue, and he said, that's fine, this is of Marcinkiewicz type, and so we were able to use the Marcinkiewicz multiplier theorem in order to show that this is nicely bounded in our space, and this allows us to sort of make all of the analysis work in this single function space, which is tooled to the stationary problem, even though we also want to do the problem for at least gamma small, but not zero. Then, of course, this is all just the understanding of the linearized theory. Now, of course, the task becomes, can you make all of the nonlinear analysis work in these weird mutant mixed type spaces? And it does if you work hard enough. And of course, the properties of this operator are what we in the end use to get the bonus estimates that I mentioned earlier for the Riese potential. And with that, I will stop and say thank you for listening.
So are there questions or comments?
Yeah. So for the first talk, you mentioned that there is an inviscid version, right? And then the traveling wave solutions.
Yes.
A lot of work in the inviscid version.
Yeah.
And then your solution.
Yeah.
Are there any connection?
Oh, not yet. But of course, this is one of, well, okay, there's a little bit at the moment. So for the full fluid equations, the answer is no yet at the moment. We don't quite have the technology, but the point is that we would very much like to do this and think that it is potentially doable, meaning we will take the solutions that we've constructed with viscosity and try to take an inviscid limit. And the goal would be, so I didn't want to say much about this because it's a bit complicated, but the solutions that have been constructed in this framework are, let's say, an absolute zoo, right? Most of these things are constructed using bifurcation theory, Crandall-Rabinowitz, and so they have these, crazy curves of solution and function space that do all sorts of, wacky stuff. And so the idea would be somehow, maybe there are certain solutions along here that can be identified as special because they can actually be achieved as the limit of the viscous problem, where of course you will need to scale the forcing in some way because you don't want to reduce to Euler with forcing. You want to reduce to unforced Euler, which is what all of this stuff is done for. So you want to somehow have a mu to some power or something like that sitting in front of these things so that they will vanish as well as viscosity goes to zero. So yeah, so have we done this? No. Would we like to do it? Absolutely, yes. With the Nash-Moser framework that we have, this is looking more and more plausible, particularly because we were able to do it here. So in this problem, I've labeled it the viscous shallow water equations, but one of the things that we're able to do is to send that viscosity parameter to zero, and to do so in some sort of continuous way.
And for the second result, how far can you go in terms of the speed, let's say gamma?
Oh, that's a great question. So admittedly, we were lazy and didn't do anything more than just say implicit function theorem gives us an epsilon that's good enough for us now. But in principle, you could work harder and try to push this to other values of to larger. I think if you worked hard enough, you could actually make the same thing work for arbitrary gamma. Yeah, I really do. There will be a little bit of non-trivial extra work to be done in handling the linear problem, but most of the nasty stuff is out of the way. So this would be an excellent problem for a graduate student. I think it should be doable, but just in some sense, we did what we wanted, and so got the stationary problem and showed it connected. So we didn't really
need some kind of global bifurcation.
We don't know. That would be a possibility for how to approach this. Though getting the precise structure needed for those, like identity plus compact or identity plus Fredholm, not so straightforward here. Especially because these domains are infinite in cross sections. So the usual tricks that you can use to get Fredholm or compact perturbations by appealing to relic or something cheap, not there.
Other questions?
For 2D, would anything change if you consider Hardy instead of L1?
Oh, presumably. I mean, this is probably the right way to go. Yeah, for sure. But yeah, now you're talking about trying to build classes of Sobolev spaces modeled on Hardy spaces rather than LP. And okay, maybe this is something that's known, but it's not something I'm familiar enough with to say that this is a believable strategy or whatever. But that is, I mean, the moral of all of this work has been fight with the problem until it tells you what function space it wants to live in and then run with that, right? So yeah, someone needs to sit and listen to what the n=2 problem is saying, and it will probably whisper Hardy space into your ear. Or some other strange space. But yeah, it's totally believable that it is doable, but you will not be doing it in standard LP-based Sobolev spaces.
In terms of the picture that you showed at the very beginning,
Yes.
the actual fluid experiments.
Yes.
In these 6 pictures, which parameter range that you can handle would go with which picture?
Well, so in this context, I would say we can actually do all of these things in the sense that, you know, so they're varying gamma. And actually, I don't think they say in the paper if they are decreasing the intensity of the wind or not.
I guess they are.
There probably are. So, okay, you know, as long as, I mean, okay, so we have an open set. So the point is that, you know, take the range of gamma that this is ranging over. And for them, this is actually over a very small range. If I remember correctly, this one is like, okay, I have no recollection of what the units are, but this is like 0.98 of those units, and this is like 1.02 or something like that. So it's
all around.
Yeah, it's all very, very close. So, you know, within our open set, if we could make it so that that full parameter regime of gamma lives in here, so, you know, 0.98, so 1.02 or whatever, there are forcing and stress couples that will be common to that set. And so actually, if whatever was acting on this was modeled by that would fall into this regime. Yeah. Now, would we be able to do that as this parameter is sent from, you know, 1.02 to 4,000? No.
You're definitely confined to your small distance.
Yes, for sure. Now, do I think that, you know, one is always confined to what you get from the implicit function theorem? Absolutely not. This is just getting our foot in the door, right? Of course, once you know the solutions are there, you can try to build up the size of the set and do more specific analysis for given speeds or whatever.
Very interesting. Other questions or comments? No? Thank you again.